How to determine soil classification. Soil classification is one of the most essential parts of any geotechnical engineering project. Before you lay a foundation or design a retaining wall, you need to know what kind of soil you're dealing with. But how do engineers actually determine soil classification?
Let's break it down step by step.
Why soil classification matters. Every structure, from a small home to a massive skyscraper, relies on the soil beneath it. If the soil can't support the load, the entire project is at risk. Soil classification helps engineers predict how the soil will behave under pressure. Will it compact? Will it expand when wet? Will it drain water effectively? These questions are answered by classifying the soil. Field identification techniques. The process usually starts in the field. Engineers collect soil samples using augers, test pits, or boring equipment. They examine the color, moisture content, grain size, texture, and smell. For example, clay often feels sticky when wet, while sand feels gritty. Quick tests like the ribbon test, rolling moist soil between your fingers, can give an early indication of plasticity and cohesiveness. Grain size analysis. One of the first steps in lab testing is grain size analysis. This involves passing soil through a set of sieves to separate it into gravel, sand, silt, and clay fractions. Coarse-grained soils like gravel and sand are classified based on their grain size distribution. Fine-grained soils like silts and clays require further analysis to understand their behavior. Atterberg limits and plasticity. To understand fine-grained soils, engineers use Atterberg limits, the liquid limit, plastic limit, and shrinkage limit. These values define the water content ranges in which soil changes from solid to plastic to liquid. The plasticity index, calculated as the difference between the liquid and plastic limits, helps determine whether the soil is clay or silty. A high plasticity index usually means the soil is clay, which may expand or shrink depending on moisture. Unified Soil Classification System, USCS. One of the most widely used classification systems is the Unified Soil Classification System, or USCS. It classifies soils based on grain size and plasticity. Soils are labeled with two-letter codes, like SW for well-graded sand, CL for low-plasticity clay, or GP for poorly graded gravel. The first letter refers to the primary soil type, and the second indicates grading or plasticity. These symbols give engineers a quick way to communicate soil properties on construction drawings. AASHTO Soil Classification. For road construction and highway engineering, the AASHTO classification system is commonly used. This system ranks soils based on their performance in supporting roadways. It categorizes soils into groups from A1 to A7, where A1 is the best for road-based material and A7 includes highly plastic clays that are generally unsuitable without treatment. The AASHTO method uses sieve analysis and Atterberg limits as inputs to determine classification. Visual aids and lab testing. During lab testing, engineers also conduct Proctor tests for compaction, permeability tests for drainage, and consolidation tests for settlement prediction. These additional tests supplement the classification system and give a full picture of soil behavior under structural loads. Visual charts like plasticity charts and grain size distribution curves are often used to confirm the classification. Why accurate classification is crucial. Misclassifying soil can lead to serious consequences: foundation settlement, slope failure, or even structural collapse. By correctly identifying the soil type, engineers can choose the right foundation system, decide on drainage measures, and ensure long-term stability of the structure. Soil classification may sound simple, but it's the foundation of everything we build.